Okay, when we talk about light, light consists of two forms. There's light acting like particles, which we call photons. That's when it's acting like matter. And then we have light acting like a wave, and we call those electromagnetic waves. The electromagnetic wave has two parts. It has an electrical part, which is an electric field that oscillates up and down or perpendicular to the direction of travel. And then we have a magnetic part that also oscillates, but this oscillates perpendicular to the electric field and the direction of travel. When we talk about electromagnetic waves, they are transverse waves. That means that the medium vibrates perpendicular to the direction of travel. And there you can see the vibration of material is perpendicular to the direction of travel. Here's a picture of the electromagnetic wave. Notice that the electric wave sits in one plane and the magnetic field oscillates perpendicular to that. Both of those are perpendicular to the direction of travel, which notice is from the left to the right on the screen. So let's talk about the parts of a wave. When we talk about a transverse wave, we usually go from crest to crest or trough to trough. And let me show you that. Right here, let me see if I can mark it. Okay, so right here is the trough, and we go from trough to trough. So we're physically measuring this distance here. Okay, we could also do it from crest to crest. Okay, so the maximum height of the wave is called a crest, right here, here, and here. And the bottom is called the trough, here, here, and here. It looks like an animal trough. The amplitude can either be positive or negative. So notice in the diagram that the amplitude here, I'm going to put it in a different color so you can see it. This would be a positive amplitude. And notice if I go this way, it would be a negative amplitude, okay? And again, the distance from crest to crest or trough to trough is your wavelength, or the length of the wave. The length of the wave has the symbol of lambda. Notice that little character, it looks kind of like an upside down Y. That's lambda, it's a Greek letter. Wavelength can be measured in two ways. It can be measured in nanometers, which is 10 to the minus 9 meters, or it can be measured in angstroms. That's that capital A with a little circle over it, and that's 10 to the minus 10 meters. And here you can see nanometer is 10 to the minus 9 meters, angstrom is 10 to the minus 10 meters. Frequency is another word we use when talking about light. Frequency is the number of cycles that pass by every second, or cycles per second. So some of you may be familiar with megahertz, like 93.7 FM. That's 93.7 megahertz. That's your frequency, or cycles per second. We also use frequency with light and radiation, and we represent that with a capital HZ for hertz. And we also say that it's also a frequency is how many waves pass by a point every second. Time period is the time it takes for one wave to pass by a point in space. Or you can also say that it's the time for one cycle to take place. There is a relationship between time period and frequency. They're inversely related, and that means that 1 over the time period is equal to the frequency, and 1 over the frequency is equal to the time period. Notice we use a lowercase f for frequency and a capital T for time period. The speed of the wave is going to be written as the wavelength times the frequency. And the formula for that is V for speed. It's not S because we use that for something else. V is equal to lambda F, where lambda represents wavelength, F represents frequency. The speed of light in a vacuum, you do need to know this because we use it quite often. The speed of light in a vacuum is represented by a lowercase c, which represents Cyrillus in Latin, which means swiftly. And it's 3 times 10 to the 8 meters per second. And here you can see when we're talking about light in a vacuum space, which we do most of this course, we're going to be using C equals lambda F instead of V equals lambda F. Okay, the electromagnetic spectrum is visible and invisible radiation. So some parts of the spectrum are going to be visible, other parts are going to be invisible to us. They may, however, be visible to other animals or other critters. So here's the entire electromagnetic spectrum. It's really important for you to understand where each part of this lies, and I usually recommend that students memorize this. So let's talk about longest to shortest. The longest wavelength range is going to be your radio range. In astronomy, the radio range usually indicates to us very, very cold things in space. So it can be dark dust clouds before they start to collapse. This is where we're going to get our radiation that's in the radio range. Go a little bit higher in or shorter in wavelength and you get microwaves. Microwaves usually indicate some type of a low energy heat. So in this sense, it could be the background radiation of the universe would be in microwaves. Next, before we get to visible, we have our infrared. Infrared is the heat that our bodies give off. Infrared is also what we're going to see when we look at dark dust clouds and we start to just see the formation of stars. So as the clouds are starting to collapse, we're going to see infrared radiation being given off. Next comes the visible range. The visible range is given off by stars and galaxies, usually the stars in the galaxies. Next is ultraviolet. Ultraviolet is even smaller than visible, and that means that it can actually get inside the atoms. Because of that, it's a little bit more high energy. We normally see ultraviolet when we're talking about the death of stars or when we're talking about supermassive blue stars. So when we talk about supermassive stars that are blue, those are giving off ultraviolet radiation. We also see ultraviolet being given off by the core of stars after they explode. So in a supernova remnant, we're going to see ultraviolet radiation as well. Once we get past ultraviolet, even more energy, smaller wavelength is going to be your X-rays. X-rays are normally given off by black holes or black hole candidates, and they can also be found for high energy events. So a supernova would certainly give off X-rays. Gamma rays are even smaller than that. And this is where we get to the really, really, really small wavelengths, very, very high energy. So a supernova that becomes a neutron star or black hole can give off gamma rays. Neutron stars, pulsars, not pulsars so much, but the neutron star, when it has material coming in it and that material gets ripped apart, that's going to give off gamma radiation. Also, black holes are going to give off gamma radiation. So that kind of gives you a guide through the universe of why we need to study the electromagnetic spectrum. Each part of it tells us different things about our universe. Okay, so let's see how this light is produced by these atoms. Okay, so if we take an electron that's in the first state, which is the ground state, and we give it a very little amount of energy. So notice right here, what you're seeing here is, let me make it a different color. Right here, this is a longer wavelength. Notice the distance between the crest to the crest. That tells me it's low energy, and so it's only going to give it a little bit of a push up to that second state or the first excited state. If we make the wavelength a little bit shorter, as you can see here, notice it's smaller, and that means more energy. We can get it to go up to the third state, n equals 3, which is your second excited state. Even smaller, we can get it to go even higher. So the more energy the photon has, the higher that electron's going to move away from, or the more it's going to move away from the nucleus. Okay, so to move it up to the first excited state, not so much energy. Second excited state, third excited state, more and more energy is needed. Okay, so as we add that energy by photons, we will cause that electron to become excited. Now, here's the thing though. Not every wavelength is going to be absorbed by the electron. The electron needs a specific amount of energy to move from that ground state to the first excited state or the second excited state. If it's not the right amount of energy, it's just going to pass by the electron. Notice in the first part it says, no thanks, wrong energy. Okay. Once it is the correct energy, though, it will go to an excited state. Notice what happens when that electron drops back down in the last slide here. You'll see it says, oops. Basically, what's happening is the electron is dropping back down to the ground state, releasing that energy. Notice, though, the direction of the light. It's not going in the same direction that it came in. This is what we call scattering. Okay, when we talk about light, we can also talk about it in terms of temperature. And so the star's color also indicates its temperature. So we're going to look at the spectral classes. These spectral classes are given to stars to tell you the temperature of the star. So in order to remember them in order, you use the mnemonic, oh, be a fine guy or slash girl, kiss me. You determine whether you're going to kiss a guy or a girl. It's up to you. So O-B-A-F-G-K-M. So it's oh, be a fine guy, kiss me. Here you can see in the chart, and this should be in your textbook also. You should be able to find a chart. I'm not going to require you to memorize these numbers, but you should look at what color the star is going to be. So if it's an M or a K star, notice it's very, very low temperature, 3,000, 4,500. And this is in Kelvin, okay? That tells me it's going to be a very red star, okay? If it's a G star, it's going to be whitish color or yellowish color. F, it's going to get more white. A, even whiter. When you get to B and O, they're going to be your blue stars. Okay, so the higher up you go in the spectral class from M to O, the higher the temperature is. The higher the temperature, the more blue it gets. So it's kind of the opposite of our the color coding on our faucets in our bathroom, right? Red usually indicates hot, blue indicates cold. In this case, it's the opposite. For light and radiation, red light is low energy, blue light is high energy. We can also use the light to tell us what elements make up that star or that gas. And so in order to do that, we need to use what we call spectroscopy. Spectroscopy is the study of spectra. Spectrum is the breaking of light into its wavelength components. And in this course, there's 3 different kinds of spectra that we're going to look at. Spectra being the plural of spectrum. Okay, so there's 3 different kinds of spectra we're going to look at. In order to see the spectra, though, we have to use what we call a spectroscope. The spectroscope is a device that takes that light and breaks it into its wavelength components. So, one, you have to have a source of light. So it could be a star, it could be a light bulb, it could be a gas cloud or an atmosphere. Next, you need a slit. The slit is used to only let a little bit of that light through. Once that light comes through, it hits a prism. That prism breaks the light up into a rainbow. Now, be careful. The rainbow is actually one type of spectra, which is called a continuous spectrum. Most spectra that we're going to look at in this course are not continuous. Next, you need a screen. The screen is where you project that spectra so that you can study it. So let's talk about the 3 different types of spectra. The first one is emission. This is what is given off by these excited electrons. So when an electron gets heated up or excited, it absorbs energy, It causes those electrons to go into an excited state, and when they drop back down, they give off their own radiation. They emit light, so that's an emission spectrum. When we look at that in the next couple of slides, you're going to see the difference between these. Please be careful and make sure that you study them. Okay, absorption spectrum is where we take a cool gas and it absorbs out the lines that it wants. But because it's so cold, that light doesn't get emitted by the star or that gas. It actually gets absorbed and then scattered again. So we call that an absorption spectrum. It absorbs that light from the source. Excuse me. The last one is a continuous spectrum, and the continuous spectrum is your rainbow. So a continuous spectrum is a rainbow of color. It's produced by a hot, luminous solid or a sufficiently dense liquid or gas. So it has to be really, really dense, like our sun is a really dense plasma, and that produces a continuous spectrum. When you're looking at these definitions, please make sure you memorize them. They will be on the quiz. So here's the way that I remember it. If I take light from a light bulb, which is a very hot, luminous solid, it's a wire that glows, that's going to give off a rainbow. An emission spectrum is different. It appears to be slices of the continuous spectrum. So again, it's this gas emitting its own lines. In other words, it's getting energy, and that energy is causing the electrons to go into excited states. When they drop back down, they give off specific colors. Now, what's really interesting is that atoms have specific colors all by themselves. So each atom has its own set of colors that it gives off, or emission spectra. This makes it really easy for us to determine what things are made of. If we take all the gases that could possibly be in a star and find the emission spectra of each one, then we can compare that to the spectra of a star or a gas cloud that's glowing, and then we can determine what it's made of. So, emission spectra are produced by excited atoms. Okay, so it has to be a very low density gas at very hot though, hot luminous gas. Okay, so here you can see it's not the light bulb in the center of this picture that's giving off the light. What we're looking at through the telescope is the fact that those atoms that are real close to the light bulb are being heated up. And that heat is causing them to get excited. And they're giving off their own radiation, okay? And that's what we're picking up. Notice that you see single lines of color in the spectra for emission spectra. Okay, now an absorption spectrum is where we have the continuous spectrum, but pieces are missing from it. Those slices we just saw on the previous slide are missing. Okay, it's produced by a cool gas that sits in front of a hot object. So in space, it could be a dark dust cloud. That dark dust cloud sits in front of a very hot star. It's going to produce an absorption spectrum. Same thing with your atmospheres of different moons and different planets. If you look at it along the side of the planet, that atmosphere can actually give off an absorption spectrum. Okay, so look at the picture, and here you can see that it's the gas in front of the light bulb. Notice that we're not looking at the top where the heat's coming around the atoms. We're looking at the cool gas in front of the light bulb. And this picture's kind of creepy about that. I mean, it's not really accurate. I would say take those lines, move them out a little bit further from the light bulb, and then you're starting to get an emission spectrum or absorption spectrum. Also notice though that you're looking at the source dead on. We're not looking at the gas, okay, which we did in the emission spectrum. Here we're looking at the hot luminous object and the gas in front of it. And notice that there's little black lines. Those lines of black indicate the chemical composition of the gas in front of the hot luminous object. Okay, so for Kirchhoff's laws, sorry, a luminous solid or liquid or a sufficiently dense gas emits light of all wavelengths and so produces a continuous spectrum of radiation. Memorize that. Okay, a low density hot gas emits light whose spectrum consists of a series of bright emission lines. These lines are characteristic of the chemical composition of the gas. Emission spectrum. Memorize that. Okay, a low density cool gas in front of a continuous spectrum source will produce an absorption spectrum. Again, this is your absorption spectrum and how it's produced. Memorize it. Okay, so for the three Kirchhoff's rules or laws, sorry, please make sure that you can identify them. On your quiz, I may change one of the words and say a low density hot gas in front of a continuous spectrum will produce an absorption spectrum. And that would be wrong. Okay, so that would be the wrong answer. So please be careful and make sure that you know the three types of spectra and how they're produced by looking at Kirchhoff's laws. Okay, spectroscopy also tells us, like I said before, the chemical composition of stars and dust clouds that are in space based on their spectra. So we look at the spectra and that tells us what they're made of. So here's a picture of probably an atmosphere. Notice that there's three dips in the curve. Those three dips correspond to the three black lines in the continuous spectrum. This tells us that it's a cool gas because they're dipping. It's not the continuous spectrum. We see the dips in front of it. So it's a cool gas, and we can see that it's made of something that has these three lines. Now, the black body spectrum tells us the temperature of the star. Remember when we went over the spectral, the OBA fine guy or girl kiss me. That comes from this black body spectrum. We're going to use the black body curve in order to tell us the temperature of things. Okay, so basically we take the intensity of the light versus its wavelength or its frequency, it doesn't matter which, and we look at the curve. And guess what? The curve always looks the same. The difference is that where it peaks will tell us the temperature of the star. Okay, so by looking at the peak wavelength or the peak frequency, we can determine what the temperature of the star is. Okay, so here are three curves. Notice that if it peaks in the blue, it's going to be very hot. And notice the bottom curve peaks in the red. Notice it's going to be cooler. Okay, so the more shifted the curve is to the blue end of the spectrum, the hotter the object is. The more it's shifted to the red end of the spectrum, the cooler it is. Okay, so please make sure you study this graph and you understand how the black body curves work. Wien's law will tell us directly the temperature of the star based on the formula. Okay, so we take the wavelength of the peak emission or the frequency, and we can get the wavelength from there, and that is proportional to 1 over the temperature. Okay, and there's actually a really great lab that I do with this. I'll also include the link into this module so you can take a look. It's not appropriate for elementary and middle school students. So if you're teaching elementary and middle school, not appropriate for them. If you're teaching high school high-end or college students, then probably they can handle it. I find that I kind of have to walk students through it, and that's at the high school level. Okay, so in this case, the temperature is going to be measured in Celsius, or it can also be measured in Kelvin. It depends on what the wavelength is. Okay, I don't know if this is going to work. We'll see. I don't think I can make these links work. I will include this link in the module for you. Okay, so let's talk about the Doppler effect. The Doppler effect tells us how objects move. It can be them moving towards us or them moving away from us. It also tells us how fast they're moving towards us or away from us. What's interesting is we're looking at the color and the wavelengths again. So by looking at the wavelengths or looking at the spectra, we can determine the direction and how fast an object is moving, either towards us or away from us. Okay, so the Doppler effect is the apparent shifting. It's not really apparent. It's the shifting of the wavelength due to the motion of the source or the listener, or both. Okay. If it's red shifted, we say that that's moving away from us. If it's blue shifted, then it's moving towards us. This is how we determine how stars move in galaxies. We look at their Doppler shift, each and every star, and that tells us over time its path or trajectory. Same thing with the motion of galaxies that are spiral galaxies. That's how we determine that they're actually rotating, is by looking at the blue shift and red shift of the stars within the galaxy. That's also how we determine where we are in our own galaxy, by looking at how the shift appears to us of all the stars around us. We can determine where we are located and how fast we're moving with respect to everybody else. Okay, so the example they always give in textbooks is a fire truck that's moving either towards us or away from us. I don't really like this example because police cars and fire trucks do not have the same tone. So when they come up towards you, it really is just that it's getting louder. It's not necessarily that you hear the Doppler effect. You can hear it more if you're watching a NASCAR race or a Formula One race. When I would say watch the movie Cars, or at least pull it up on a video. Maybe I'll pull it up for you. When you hear the car come towards you, it's and then that's increasing the pitch, which is increasing the frequency. As it moves away from you, we hear notice how it goes from a high pitch down lower. Okay, so that's the Doppler effect. As it moves towards us, the pitch gets higher, the frequency goes higher. As it moves away from us, the frequency gets lower. Okay, so for light, it's the opposite. I'm sorry, it's the same, but notice how when it's moving, the source is moving towards us, it scrunches up that wave, which makes it blue, right? Smaller wavelength, blue. As it moves away from us, the wavelength spreads out. As it spreads out, it becomes longer, which means it's red shifted. By looking at how much it's scrunched or looking at how much it's elongated, we can determine the actual speed of the object. Okay, I'll again post a video to show you how we determine the Doppler effect and how much we determine it. This example just shows you a physical picture of it, but it doesn't show you the spectra. And so in the video link I put up on the course, you're actually going to see how that light spectra shifts.